October 29, 2025. Earth's telescopes go blind as the most massive interstellar object ever seen, 3I/Atlas, slips behind the Sun. Official reports call it a routine comet, but the numbers don't add up. A nucleus 20 kilometers wide, 33 billion tons in mass, discovered before any predicted swarm of smaller cousins. Scientists panic because this blackout is timed with the one moment Harvard's Avi Loeb warns could let Atlas perform a hidden maneuver to trap it in our solar system forever. For 6 weeks, no one on Earth will know what's happening. What exactly is being concealed during the solar blackout, and what will we find when Atlas emerges? July 1st, 2025. The Atlas Survey telescope in Rio Hurtado, Chile scans the southern sky, searching for anything out of place. Just after midnight, the automated pipeline flags a moving point, faint, fast, and on a course no known comet or asteroid should follow. Within hours, astronomers at the control room realize the numbers don't fit any familiar pattern. The object's apparent brightness, even at a distance of nearly 3 astronomical units, suggests a nucleus nearly 20 kilometers wide, unprecedented for a first sighting. Initial orbit calculations, using positions from both ATLAS and pre-discovery data from Zwicky Transient Facility, reveal a hyperbolic trajectory. The object is not bound to the Sun. It is coming from deep interstellar space, with a velocity that guarantees it cannot be a solar system native. That status, 3I, the third interstellar object ever confirmed, lands within days as minor planet center bulletins circulate to observatories worldwide. The official designation, 3I/Atlas. Inside the Atlas control room, the mood swings from routine to electric. The previous 2 interstellar discoveries, Oumuamua and Borisov, were both small, faint enough to escape detection until they were nearly gone. This one is different. Its size and mass, estimated at over 33 billion tons, dwarf anything in the survey's database. The principal investigator describes it as finding a blue whale before ever seeing a sardine. Pre-discovery images now combed from other sky surveys show the object's faint track stretching back to mid-June. Each frame confirms the same story: a giant, moving too fast and too straight to belong here. The control team triple-checks the astrometry, ruling out software glitches, misidentification, or catalog errors. Every check tightens the fit: hyperbolic orbit, interstellar origin, and a scale that defies expectation. Within a week, the world's major observatories pivot to track 3I/Atlas. Early photometry and positional data pour in, each new measurement reinforcing the sense of anomaly. The discovery is not just a scientific milestone, it is a statistical shock. Survey models predict that for every giant like this, thousands of smaller, fainter interstellar objects should have been found first. Yet, the first clear, unambiguous detection is the biggest of them all. The question is no longer if the numbers are right, but how such an outlier could appear before its supposed kin. That contradiction leads directly to the next mystery: why did the surveys catch the giant first? Population models are built on power laws, mathematical rules that describe how many small objects exist for every giant. In every known group of asteroids, comets, or planetary fragments, the pattern holds. The bigger the object, the rarer it should be, and the odds of finding a true colossus first are vanishingly slim. Surveys like Atlas, Pan-STARRS, and Vera Rubin have spent years scanning the sky, logging thousands of faint streaks, each one a possible visitor from beyond the solar system. Their sensitivity reaches down to objects just 50 meters across, smaller than a city block. Yet, for all this effort, the very first unambiguous giant is a 20-kilometer-wide nucleus, weighing in at 33 billion tons. The numbers are stark. For every interstellar object as massive as 3I/Atlas, models predict at least 10,000 smaller cousins should have passed through the inner solar system, quiet, dim, and far more likely to slip past unnoticed. Instead, the only two earlier interstellar discoveries, Oumuamua and Borisov, were both tiny, less than a kilometer across. Atlas, by contrast, is a city-sized anomaly, its brightness and mass confirmed by independent photometry from Zwicky Transient Facility, the Vera Rubin Observatory, and dozens of follow-up stations worldwide. The principal investigator at Atlas put it bluntly, "It's like finding a blue whale before ever seeing a sardine." Statistical simulations run by the survey teams reinforce the improbability. Monte Carlo models, sweeping through every possible population curve, return the same answer. The chance of detecting an object this large first is less than 1 in 10,000. The odds strain belief, especially given the relentless search for smaller bodies. Even the survey's detection biases, favoring brighter, slower objects, cannot account for the absence of a swarm of minor interstellar debris. Each new data point tightens the paradox. The mass estimate is not a fluke. It's derived from the object's brightness, its distance, and the way sunlight glints off its icy surface. The margin of error is narrow, the conclusion inescapable. If the models are right, the solar system should be teeming with smaller interstellar visitors. Yet the first clear catch is a giant. The question is no longer about detection limits or survey gaps. It's about whether something fundamental in the models or in the nature of 3I/Atlas itself has been missed. The stakes rise from statistical surprise to a challenge for the physics that underpins our understanding of the cosmos. Despite the unmistakable signs of activity, jets streaming from the nucleus, a coma swelling with vapor, 3I/Atlas refuses to budge from its predicted track. In Comet science, outgassing is more than spectacle. Every kilogram of escaping gas should act like a thruster, nudging the nucleus ever so slightly off course. For typical comets, even modest activity leaves a trace in the astrometric record, a slow drift, a subtle curve away from gravity's pull. But the global dataset for Atlas, spanning 122 published positions from 31 observatories by July, with more expected but not yet released, finds no such deviation. The upper bound on non-gravitational acceleration sits below 15 meters per day squared, a limit so low that only a truly massive inert object could remain so unmoved. The numbers are relentless. Outgassing rates, estimated at 100 to 150 kilograms per second, should have produced a measurable push. The Minor Planet Center's orbital fits, cross-checked by JPL and independent teams, show residuals in the tenths of an arc-second, well within the noise, but not enough to hide any real acceleration. Monte Carlo simulations, running thousands of alternate scenarios, confirm that for anything smaller or less dense than the current estimates, Atlas would have veered off its hyperbolic path long ago. The absence of this rocket effect is not a matter of poor data or observational gaps. It's a direct contradiction of cometary physics as understood from every other known object. Alternative explanations strain the imagination. Symmetrical jets firing in perfect opposition, a swarm of loosely bound fragments balancing each other's thrust, or a crust so thick and inert that gas vents leave no mark. All require fine-tuned conditions never observed before. The more plausible answer, at least for now, is mass. A nucleus so large and dense that even hundreds of tons of escaping gas barely register. Yet this solution only deepens the mystery. If Atlas is truly as massive as the photometry suggests, it stands alone among known comets, solar system or interstellar. Every question about natural escape or engineered stability, about comet or artifact, hangs suspended in this absence of motion. The next clue lies not in the numbers themselves, but in the chemistry driving the jets. Textbook comets are built from water ice. frozen relics of the early solar system, their chemistry shaped by cold and distance. But when the first spectra of 3i/Atlas arrived from the Very Large Telescope and JWST's NIR spec in August, the results upended every expectation. Instead of a familiar blend, the coma was flooded with carbon dioxide, 8 molecules for every 1 of water vapor. That ratio stands on its head the pattern seen in every other well-studied comet, where water dominates and carbon dioxide is a trace. The numbers are not a quirk of a single instrument or a fleeting outburst. Multiple nights of data, overlapping coverage from ground and space, and careful cross-checks with calibration stars confirm the finding. At 3.5 astronomical units, water should sublimate first, yet it barely registers. The spectral fingerprint at 4.26 microns, carbon dioxide signature, dwarfs the weaker water bands, even as the comet brightens and jets fire from its sunlit hemisphere. For context, the average Oort cloud comet, like C/2014 Q2, Lovejoy, displays a carbon dioxide to water ratio near 1:4. Atlas reverses that, with carbon dioxide overwhelming water by a factor of 8. No known solar system body, not even the most peculiar centaur or scattered disk object, comes close. The finding forces a reckoning with formation models. In the coldest reaches of a protoplanetary disk, carbon dioxide can condense, but only if water is already depleted or lost, an environment foreign to our own solar system's history. Some theorists suggest a birth in a carbon-rich, oxygen-poor nebula. Others invoke radical processing by cosmic rays in the interstellar medium, stripping water and leaving dry ice behind. Yet, neither scenario predicts the sheer abundance measured here. The implications ripple outward. A carbon dioxide-dominated inventory changes how the nucleus responds to sunlight, altering jet strength, coma structure, and even the color of scattered light. It hints at a thermal history and chemical pathway unlike anything cataloged. The possibility of artificial processing, deliberate or incidental, cannot be dismissed, though no direct evidence points that way. For now, the only certainty is the anomaly itself, written in starlight and confirmed by the universe's most sensitive eyes. Every attempt to fit Atlas into the familiar mold of a dirty snowball fails on this basic chemical test. The next stage of the puzzle lies in the path it carves through the solar system, and whether its composition signals a new class of interstellar visitor or something stranger still. Trajectory maps for 3i/Atlas reveal a path that defies the odds. Instead of plunging through the solar system at a steep angle, this interstellar giant threads a corridor just 5 degrees off the ecliptic, the same plane traced by the planets. Such alignment is not a quirk of perspective. Most comets, even those born here, tilt and twist through space, their orbits shaped by ancient collisions and gravitational tugs. For a visitor from the stars, the expectation is chaos, a random slice through the planetary disk. Yet Atlas glides almost parallel, as if following a route mapped out in advance. The improbability compounds with each planetary encounter. On October 3rd, Atlas sweeps within 29 million kilometers of Mars, a margin that by interplanetary standards counts as a near miss. The trajectory then draws it close to Venus, and after the blackout, onward toward Jupiter in March. Each flyby stacks the odds against coincidence. Orbital dynamicists run the numbers. The chance of a hyperbolic object this massive threading such a sequence is less than 1 in 1,000. The geometry reads less like accident, more like a mission profile. Every question about natural randomness or engineered intent hangs on these alignments. The planets become silent witnesses, their gravitational fields offering both obstacles and opportunities. With each close pass, the possibility grows that Atlas's path is more than just a product of chance. The next vulnerability lies ahead, when the comet slips behind the sun and observation goes dark. What happens in that blind spot may decide whether Atlas leaves or stays forever. October 29th draws a hard line across the calendar. On this day, 3i/Atlas reaches perihelion, its closest approach to the Sun just 1.36 astronomical units out. The geometry is relentless, Earth, Sun, and Comet locked in a straight line, with our planet stranded on the far side of the glare. No ground-based observatory can separate the faint glow of Atlas from the solar furnace. Even the most advanced space telescopes, Hubble, JWST, and SphereX, are forced to stand down, their safety protocols triggered by the risk of pointing too close to the Sun. The practical result is a 6-week blackout, stretching from late October through early December. Astrometric tracking, spectral analysis, even basic brightness measurements all go dark. This is not just an inconvenience. The blackout falls at the exact moment when the comet moves at its highest velocity, 44 kilometers per second, skimming through the most gravitationally sensitive part of its path. The timing couldn't be more precise. If any course correction were to happen, this is the window. Dynamicists calculate that a delta 5 of just 8 kilometers per second applied near perihelion would be enough to snare Atlas into a bound orbit, transforming it from a fleeting visitor into a permanent resident of the solar system. Mars orbiters, Solar Orbiter, and even Bepi Colombo scramble for a glimpse, but their vantage points and shielding leave them nearly as blind as those on Earth. For the first time since discovery, the world's best instruments fall silent, and every question about Atlas's fate hangs in the enforced silence. The blackout is total, perfect cover for whatever might unfold, unseen on the far side of the Sun. Records vanish from public databases just as the blackout begins. On October 12th and again on the 27th, Minor Planet Center logs for 3I/Atlas are flagged for pending validation. Key astrometric entries disappear, with archive snapshots confirming the gaps. The timing is impossible to ignore. In the same window, classified briefings ripple through government agencies, according to leaks later published by the debrief. Official explanations cite routine data quality checks, but research forums ignite with speculation. Is this scientific caution or institutional gatekeeping? Spectral anomalies deepen the sense of unease. In late September, observers report a forward-facing sunward glow, an auroral haze leading the nucleus, bright enough to puzzle even veteran comet hunters. Then, just before the blackout, it fades without warning. Almost simultaneously, a surge in green emission, normally a late-stage marker of volatile release, peaks weeks ahead of model predictions. Both phenomena defy textbook comet behavior, and both are left unresolved as the comet slips behind the Sun. Into this vacuum, the scientific conflict sharpens. Avi Loeb, never shy about challenging consensus, pushes the capture theory. If Atlas executes a maneuver now, the blackout provides perfect cover. Tom Statler, representing NASA's official line, remains unmoved. It looks like a comet, does comet things. Every contradiction, every missing data point, every unexplained flare stacks the suspense. The world waits for December, when Atlas re-emerges and the sky's silence breaks. Proof or dismissal, 6 weeks of enforced ignorance will decide which side history remembers. On July 1st, 2025, astronomers confirmed 3I/Atlas as the largest interstellar object ever detected, 20 kilometers wide, 33 billion tons, and on a hyperbolic path. Its statistical improbability, zero measurable non-gravitational acceleration, and an 8:1 carbon dioxide to water ratio set it apart from any known comet. Yet, just as it reached perihelion on October 29th, every major telescope on Earth and in space was forced to shut out its signal for 6 weeks, leaving a critical data gap. Official records flagged on October 12th and 27th remain classified, and key emission anomalies remain unexplained. As 3I/Atlas emerges in December, only its orbital track, hyperbolic or captured, can settle the debate between scientists like Avi Loeb and NASA's Tom Statler. Until then, the facts are clear. The world's largest interstellar visitor vanished behind the sun with more questions than answers, and what returns may challenge every assumption about what moves through our solar system.